If you remember, we talked last time about something called the intermediate value theorem. And this theorem looks very innocent, but it's actually very powerful. I'm just going to tell you again what it is. Suppose that you have a continuous function so you have a continuous function defined on the interval a to b. And you have a number n that lies somewhere between f of a and f of b. So you have these 2 points, f of a and f of b, in a sense the extremes, the vertical extremes of the function, or not necessarily, but you can think of it that way. And you have a point n between them, and you draw a horizontal line on the graph. Now, is it reasonable to say that this horizontal line must intersect the graph? Well, yes, right? Because the function is at some point at a, it lies over down here, and at b, it lies over up there. So at some point, the argument goes, it must have crossed this horizontal line. And that is basically what the theorem says. It says at some point, the graph of the function crosses this horizontal line. Technically speaking, what we say is that there exists a point c between a and b such that f of c is equal to n. If you think about it, having a point such that f of c is equal to n is the same thing as crossing the horizontal line, because at that point you're touching the horizontal line, right? Okay, so great. Let me say a couple of things. First of all, the proof is highly non-trivial. The proofs of everything else we've said in the class, while not obvious, you could write on the paper with just being generally smart and thinking about things precisely. This thing would require a course on some other total different types of concepts, such as topology. Basically, you will prove that the interval from a to b is what we call compact. I'm not going to get into details, but it's a non-trivial proof. And also, it is not true for discontinuous functions. Not true if f is discontinuous. What could happen if the function is not continuous? Well, what could happen is something like this. Here's a, here's b, and you have a discontinuity in the middle, and if you choose n to be right in the middle, there's not going to be any point c such that f of c is equal to n. So in a sense, this theorem describes a profound property about continuous functions. So what is this theorem good for? Well, the theorem is used for finding roots of equations. What do I mean by that? Okay, so for example, suppose that I write the equation e to the x equals cosine of x plus 1. Now, if this was a different type of equation involving, I don't know, x squared or something like that, you can always try and solve for x. Right? You can multiply things around, do some algebraic procedure that will get rid of all the x's except for 1, and then you write x equals so on and so forth. That is solving the equation. But in this case, you have both an e to the x and a cosine of x. The two of them together are very inconvenient. There's really no way to multiply things around to get rid of that cosine and that e to the x. If you take logarithms on both sides, you'll get rid of the e to the x, but you won't get rid of the cosine. And you can put the other stuff on the other side and take, let's say, cosine arc cosine or cosine minus 1, but you still have the e to the x. So you cannot really solve for x. However, using the intermediate value theorem, you can prove that this equation has a root. Even if you don't know exactly where it is, at least knowing that it exists can be a very powerful thing. So, prove that there is a solution between 0 and pi. So not only does the equation have a solution, but the solution, or at least one solution, must lie between 0 and pi. Let's see. So how do we do this? Well, we want to use this theorem. So we're going to have to come up with some function, f of x. And I'm just going to bring this stuff over to that side and set f of x to be equal e to the x minus cosine of x minus 1. Okay, so let me ask you guys. If I find a point such that f of x is equal to 0, what can I say about that point? Let's say that f of 3 was equal to 0. What can I say about the number 3? It's a 0 of the function, yes. And what is it also? It's a root of the function, and it's a solution of the equation. You guys agree? Awesome. So we're now down to finding what we call a root of the function f. In other words, a point x such that f of x is equal to 0. Now, first of all, point out that f is continuous. How do I know that? Can anybody remind me from last lecture how I know that this function is continuous? Yes?
Either x is continuous and cosine x plus 1 is continuous.
Okay. So when you add continuous functions, you get a continuous function. Right? Excellent. Thank you, sir. What's your name? Sorry?
Jesse.
Thank you, Jesse. All right, so that's the first thing. Now the second thing is we want to evaluate the function at different points. For example, at 0, the function has value e to the 0 minus cosine of 0 minus 1. So e to the 0 is 1, cosine of 0 is 1, and this is minus 1, so the whole thing is 1 minus 1 minus 1 is equal to minus 1. I'm also going to evaluate f at the point pi. And I'm going to tell you in a moment why we're doing this. That's e to the pi minus cosine of pi minus 1. What's cosine of pi? It's minus 1. So this turns into a plus 1 minus the 1 becomes 0 is e to the pi. Okay? So you can think about the function. Let me make a drawing of this thing. Here's 0, here's pi. At 0, the function has value minus 1. At pi, the function has value e to the pi, whatever that is. It's actually something like 23.1. And the function is continuous. So I'm not sure exactly how this function looks like, but do you see on the graph that the function has to have value 0 at some point? It's obvious, right? At some point, the function must have value 0. So we say mathematically by the intermediate value theorem, set n equals 0. So your n is equal to 0. And notice that 0 is less than e to the pi and is bigger than minus 1. Okay, so we're satisfying this condition. N lies between f of a and f of b. Okay? So there exists C between a and b, between 0 and pi, such that f of c is equal to 0. That's where we apply the theorem. And by setting f of c equal to 0, we can say that e to the c, you just replace f of c by the expression, e to the c is equal to cosine of c plus 1. That's our root. Question? No questions? Let me move this off, hold on. Great. Well, now, let's start with what we were supposed to talk about today, which is section 2.6. called limits at infinity. Okay? So we had already talked about something called vertical asymptotes. What's a vertical asymptote? It's one of these things, right? It's a dotted line such that the function gets closer and closer to the line. Right? We call this thing a vertical asymptote. Asymptote. Okay, asymptote sounds Greek, and it's a Greek word. It's not a word you see very often. I actually looked it up, and this morning I checked what it means, and it turns out there's a verb called ptotos, that's to fall. So like ptotos, right? And symptotos means to fall together. Like, you know, if two things fall together, that's symptotos. And asymptotos means that it does not fall together. So it all makes sense, right? No, it still doesn't make sense. The reason, I don't know, it's a weird name really, because it means that the vertical line and the function do not fall together. In other words, they never actually touch each other. The name asymptote just refers to the fact that the two of them don't touch. But I think more important than them not touching is that they get closer and closer and closer. Right? So, yeah, those Greeks should come up with a better name than that, I think. Anyway, so that's a vertical asymptote. And we already talked about this algebraically. What does this mean algebraically? This part over here. It means that the limit, let's say that this point is a point 2. Can anybody tell me how to write this down mathematically? Yes?
As the limit approaches 2 from the positive side,
Okay.
it gets to infinity.
As the limit approaches 2 from the positive side. So limit when x goes to 2 plus of f of x is equal to infinity. That's right. And that's a vertical asymptote. We already talked about it. But now we're going to talk about something called a horizontal asymptote, which graphically is the same thing but horizontal. It means that the function becomes closer and closer and closer to that value and never actually touch it. Okay, so how do I write this? This is written, let's say that this point is 4. Okay? So the way we write this is that the limit when x goes to infinity of f of x is equal to 4. It's pretty much the same idea as before. This thing is called a horizontal asymptote. Horizontal asymptote. Once again, the name doesn't even make sense in Greek. And in general, I can write the limit of f of x when x goes to infinity is equal to L, means that as x grows arbitrarily, so as x becomes 10, 100, 1,000, and so on and so forth, f of x approaches L. Awesome. Question? What about, can we do x goes to minus infinity? Can we do that too? Yes, we can. Limit when x goes to minus infinity of f of x equals to L is the same thing as x becomes, let's say, bigger and bigger but negative. So minus 100, minus 1,000, f of x approaches L. Great. So that's, you might notice that we're doing the same thing over and over again. We started by talking about functions in two different ways. We say there's functions that, you can draw them. You can recognize the function by drawing it. Or you can recognize a function by a formula. And there's also the Mickey Mouse representations of functions, which are tables and bags, you know, these Venn diagrams or sets. So, but the real, let's say the more useful ones are graphs and equations. So every time we talked about a concept, I've tried to draw it first graphically and then using equations. And we did this with continuity, we did this with limits, we did this with asymptotes, and now we're going to do this again with horizontal asymptotes. So you can see in the graph what a horizontal asymptote is. Now let's talk graphically what a function, how to compute the limit of a function when x goes to infinity. So example, the limit when f goes, I'm sorry, f is just going to be, let's do a really easy one. X goes to infinity of 1 over x. Who would like to explain to me what that is and why? Yes?
It's 0 because 1 over infinity is going to approach 0.
Okay, I like that, but you should be a little bit more precise. You cannot actually set x equal to infinity on the bottom, okay? That's exactly right. As x becomes bigger and bigger and bigger, the bottom part becomes larger and larger and larger. Okay? So it's not like you can set this equal to infinity, but you can say, and I'm going to write it sometimes, you can see that this thing goes to infinity. Because the thing on the bottom goes to infinity, and the thing on the bottom, on the top is 1, the whole fraction is equal to 0. Okay? Awesome. Let's do one slightly more complicated one, and you'll start seeing a method to this whole thing. So let's see. Limit when x goes to infinity of x squared plus 1 divided by 2x to the 4 minus 3. Okay. So let's say that we do the same thing as before. We evaluate x equals, I don't know, 10, 100, 1,000, and every time we plug it in up and down. Then what happens? The thing on the bottom becomes bigger and bigger, as before, but the thing on the top also becomes bigger and bigger, right? So that's no good, because it means that the top goes to infinity, and the bottom goes to infinity. So what does the whole thing converge to? Yes? Ah, I like that. The bottom goes to infinity faster. That's very good. Yes?
I can solve it mathematically. Divide both by x squared. And then 1 over x squared is 0 and 3 over x squared is 0.
Okay.
It's 1 over.
That's excellent. So, what's your name again? Edim? Okay, Edim is suggesting a very nice trick, which is to divide up and down by some power of x. Okay? Edim is suggesting x squared. But to be more consistent, I'm just gonna propose as a general trick to divide by the largest power in the whole thing. What is the largest power in the whole thing? X to the 4th, right? So I believe, Erin, that you can do the same thing with 1 over x squared in this case, but just to be consistent, let's multiply by 1 over x to the 4th up and down. Okay? And of course, that doesn't change the expression, so that's equal to the limit when x goes to infinity of, and what do we get? Here we get x squared divided by x to the 4th is 1 over x squared, right? Plus 1 over x to the 4th, okay? Divided by 2, because the x to the 4 cancels out, minus 3 divided by x to the 4th. Now let's try this again. The thing on the top goes to what? The thing on the top goes to 0, because as x becomes larger and larger, 1 over x to the 2 and x to the 4th become smaller and smaller and smaller. So the thing on the top goes overall to 0, and the whole thing in the bottom overall goes to what? To 2, that's right. Because when x becomes really, really large, think about x equal 1,000. 1,000 is not really, really large, but it's pretty large. X to the 4th is a very large number. So 2 minus 3 to the x to the 4 becomes very, very small, and the whole thing goes to 0. Sorry, not to 0, to 2. This part goes to 0, this part goes to 2. Okay, so if the top goes to 0 and the bottom goes to 2, then the whole thing goes to 0. That's right. Okay, in this case, I can set 0 divided by 2. I don't really like writing 0 divided by infinity, but it might be okay. I just want to make sure you understand that you cannot really actually set x equal to infinity. But I think this notation is fine. It's maybe a little bit more precise. Okay, so can we use that in general? Let me write down the trick in general. In general, a useful trick is to divide by the largest power. For rational limits. Do you remember what a rational function is? It's a fraction of two polynomials. Right. Let's do another one of these. Limit when x goes to minus infinity of 2x to the 3 plus 1 divided by x to the 3 minus 4x squared. Okay, so it gets more complicated. Now think about what happens when x becomes very, very large and negative, like minus 1,000. So the thing on the top becomes what? Very large and negative, right? The thing on the bottom becomes very large and negative too. So we got something that goes to minus infinity divided by something that goes to minus infinity. Once again, we cannot determine just by looking at it what the value is. And I should have said this before. Infinity over infinity is not determined. It could be equal to 0. It could be equal to infinity. It could be equal to 5. Okay, so when you have a limit where the top converges to infinity and the bottom converges to infinity, you don't know what's going on. You have to rephrase it. Same thing, if the top goes to 0, the bottom goes to 0, you have to rephrase. You don't know how it works yet. So what are we going to do? Well, we're going to use the same trick as before. X goes to minus infinity of, I'm going to multiply up and down by 1 over x to the 3. That's right. You guys got it. 1 over x to the 3. Okay, and of course you have to multiply every single term. So this becomes 2. This becomes 1 over x to the 3. This becomes 1. This becomes 4 over x. Right? Because x squared divided by x to the 3 is 1 over x. Okay. So what happens with the top? This becomes smaller and smaller, but it's added with 2. So the top goes to 2, and the bottom goes to 1. That's right. What about this minus infinity? Does it matter? No. Because whether x is positive or negative, 1 over x becomes very, very small when x becomes very, very large. Either large and positive or large and negative, doesn't matter. You do have to think about it, but in this case it doesn't really matter. And so this is 2 divided by 1 is equal to 2. So look at that. That's a good example of what I was saying a moment ago. You have something that goes to infinity divided by something that goes to infinity, and the limit is 2. Weird, right? You would think the limit has to be either 0 or infinity, but no, it can be actually 2. Any of those things can happen. Do you have any questions? Okay. Okay, so next. I'm going to give you one more such limit. Yeah. Okay. So limit when x goes to infinity of square root of 4x squared plus x minus 2x. Okay, we have not seen this kind of limit before. Is it limit of a sum? Well, a subtraction in this case. Let's take it as two different things. We're taking this guy here and we're subtracting this guy here. As x goes to infinity, what does this converge to? What do you think? Well, 4x squared plus x becomes really large. What if I take the square root of that? The square root of that? Still very large, right? So this thing by itself goes to infinity. And of course, 2x goes to infinity. So we have infinity minus infinity. Infinity minus infinity. Can we tell what the answer is from just seeing infinity minus infinity? Is that 0? Once again, it's an undefinite form. Just by looking at it, you cannot tell what it is. So we have to rephrase. We have to rephrase. We have to do some trick, some algebraic, something or other. Do you guys have any ideas?
You can actually do the square root. At least you can partially do the square root.
The square root of what?
Get rid of the radical.
Okay. That's a good idea. Let's think about how we could get rid of the radical. Yes?
Multiply it by the square root of 4x, then plus 2x.
Yes, very good. Are you also thinking in terms of trying to get rid of the radical? Okay, that's a very good idea. So how do we, well, I'm just gonna rephrase what you said. The idea is to multiply by the same thing but plus 2x instead of minus 2x. So when we multiply this by, let's say, square root of 4x squared plus x plus 2x instead of minus, then this thing becomes 4x squared plus x minus 4x squared, which is great. But there's this principle of conservation of, I don't know, something. You cannot just add 1 to, or multiply by 5 your expression, right? You're going to change the answer. So if we want to preserve the answer, what do I have to do? I'm going to multiply up and down by the same thing. Okay. So it's a similar trick that we did before. If you notice, we're really only using a limited number of tricks. We're multiplying by, we're dividing by the biggest degree. We are multiplying by what we call the conjugate. This is the conjugate of this expression. Okay, what's this then? A minus b times a plus b. A minus b times a plus b is equal to a squared minus b squared. Can you see that? A minus b times a plus b is equal to a squared minus b squared. So in this case, it's this expression squared is 4x squared plus x minus this expression squared is 4x squared divided by square root of 4 x squared plus x plus 2x. Great. We're hoping that something's going to cancel out here, and in fact it does. This thing cancels with that. So we end up with an x on the top and something more complicated looking on the bottom. All right, but now what? Are we done? No, not yet. Unfortunately, it's not done yet. The top part is x. The top part goes to infinity, right? The bottom part goes to infinity. That's right, Arik.
Just a bit faster.
Well, Arik suggests that maybe it goes faster on the bottom than the top. I don't know. So how do we figure that out? We haven't actually done this one before. Let me write it again. X divided by 4x squared plus x plus 2x. Okay, so this is not quite what we had before because it has a square root. The largest exponent on the top is x. And what about the largest exponent on the bottom? Well, there's an x squared, but it's inside a square root. So it's almost like the largest exponent on the bottom was also x. Okay? It's not obvious, but if you have something squared inside of a square root, it's more or less like the largest exponent is x. Be it as it may, we're going to try out multiply by 1 over x up and down and see what happens. Okay? So let's try this idea of doing the same thing as before. I'm sorry, not x squared, by x. Okay, let's see what happens. Okay, on the top we get 1, right? Easy. What about the bottom? Well, the bottom is 1 over x 4x squared plus x plus 2. Okay, and now I can write that 1 over x as the square root of something so that I can bring it inside the square root. So 1 over x is the square root of what? The square root of x squared. Okay? 1 over x is the square root of x squared. So the square root of one thing times the square root of another, I can write down as the square root of the whole thing. This is 4 times, this thing divided by x squared plus x divided by x squared is 1 over x plus 2. Is that clear, or should I say it again? All right, so this is the square root of, basically over here there was a 1 over x. I want to write it as the square root of something so that I can bring it together inside of the square root over here. So I'm writing this as square root of 1 over x squared. So the first thing is to realize that this thing is just 1 over x. Now, this thing is equal to the square root, so 2 square roots multiplied is the same as the square root of the whole thing. The square root of 1 over x squared multiplied by this expression inside. And once I have it multiplied, I can multiply out. And this is 4x squared divided by x squared plus x divided by x squared. That's how we got here. Okay, now the top part continues to go towards 1. And the bottom part goes towards what? As x goes to infinity.
4.
That's right, it goes towards 4. That's because this thing goes to 0. The square root of 4 is 2. And plus 2 is 4. So, if you go back to the beginning, you have this expression, infinity minus infinity. The last thing you thought is that the whole thing goes to 1/4. But there you go. Okay? So this limit is 1/4. Questions? Yes? Sorry, say it again?
I still don't get why you put a square root over 1 over x.
Let's do this again here in the bottom. Oh, you mean why this, when we multiply by 1 over x, this is equal to this?
No, like we put a square root over it after that. We put a square root over it, and then we put it underneath it.
She's talking about the second one.
Okay, from here to here? Okay, so in general, the square root of a times the square root of b plus c is equal to the square root of a multiplied by b plus c. Okay, and this can be multiplied out as square root of a b plus ac. In this case, a was 1 over, 1 over x squared, and this is b and this is c. Better? Okay. So also this exercise confirmed that when you have an expression like 4x squared plus x, the largest degree is x squared divided by 2. In other words, the square root of x squared is equal to x. Okay, it's just a thumb rule. It's nothing particularly precise. The bottom line is you can multiply by different things, different exponents of x, and see which one works best. And in this case, the largest exponent is more or less x. Okay, any other questions? All right, so I'm going to mention one last thing, and that is so infinite limits at infinity. For example, suppose that we look at the function f of x equals e to the x. The limit of e to the x when x goes to minus infinity is what? It's 0, right? Okay? Great. This is nothing new. This is what we just did. What about the limit when x goes to infinity of e to the x? Okay, this one is new because we haven't done this. We have only talked about asymptotes, and in this case, there's not really any asymptote. This statement here, the limit when x goes to infinity of e to the x is infinity. The only thing this is saying is that as x becomes really, really large, e to the x becomes really, really large. That's really all it's saying. It's a pretty easy statement to make. So in general, limit when f of x when x goes to infinity is infinity means as x grows arbitrarily, f of x becomes arbitrarily large. Okay, now there's a whole bunch of combinations here that you can also look at. The limit when x goes to minus infinity, the limit when x goes to infinity is equal to infinity or minus infinity. There's actually 4 combinations. Let me write them down. So x can go to plus or minus infinity, and the limit could be plus or minus infinity. So there's 4 different statements there. You should know what each of them means. And it's basically the same thing. Okay, questions? All right, so in the last 3 minutes, I'm going to say something. I think we're not going to talk about limits per se very much anymore. So I would like to say something we didn't really touch before. And is that, does any function not have a limit? Can a function not have a limit? Well, what do you think? We talked about a function not having a limit. Let's see. We said that a function may not have a limit in this situation, for example. Okay? So the limit from the left exists, the limit on the right exists, but they're not the same. So the limit overall does not exist. Right? But that's kind of cheating because the limit on the right does exist. What about a function that does not have a limit from the right? Doesn't even have a limit at all? What do you think? So is there a function that does not have a limit, let's say when x goes to 2 plus? Even if you just look at one side. As it turns out, there is. If a function looks like this, let's say that this is a. If a function does something really weird like this, right? Then you cannot say at x, as x goes to a from the right, you cannot say that f of x converges towards anything. It just keeps oscillating up and down like crazy. Right? Can you give me an example of such a function? F of x equals, yes? 1 over x plus 2. Well, actually, not quite. If you draw, you're talking about 1 over x plus 2, right? Okay, 1 over x plus 2 is the horizontal translation of 1 over x. So it looks pretty much just like 1 over x. It's just that it got moved by 2. So it has the same shape. Yes?
Sin x.
Almost. Sine of x, as you know, is a wave. It doesn't really have that shape. But you can do something to the sine function.
1 over sine x squared is correct.
1 over sine of x squared. No, it's easier than that. Let me show you. Sine of 1 over x. Okay? So, you know that the sine function has a regular wavy pattern. As x becomes really, really large, well, let me just say this. As 1 over x becomes really, really large, the function starts moving up and down faster and faster. So as x becomes closer and closer to 0, the function sine of 1 over x starts oscillating faster and faster and faster. So this is 1, this is minus 1. And you can't even draw this thing because it starts oscillating so fast that the paper is not good for trying to draw it. But there you go. Okay, any other questions? No questions. Okay, we're going to stop here. See you next class.